the situation is not that good as such right now.
Mm.
Um, it's improving, but not as good as we thought. And there is a lot of like new cases, right? I think you might be knowing about the new cases. Every day is building up,
Yeah, yeah. Mm.
and it's like we have to do three times. And like since I come to office, we have to do like three times a month. We have to do a COVID test, which is annoying.
Wow.
Yeah,
Gosh. Okay. Okay.
and of which one was that swab one, which is so irritating. Other
I
two is
don't
like
know. Fortunately, I have not got one done yet.
I have done swab as well as a saliva test, and it's like annoying.
Oh dear. Okay. Okay.
Yeah.
But this is something that the university has mandated, or what is the kind
So
of reason for
university
this?
asks you to fill the form that you are in the office,
Okay.
and also it tells you that that you have to do a COVID test, twice a month. That's what they say, and so your actually your presence is recorded every other day. So if I'm
I
coming
see.
today to office today, so it will be recorded. So that means that if you are unhealthy, you need to report. That's a mandate. If you are
Right.
not, then your entire privileges and access will be revoked.
Wow.
So
Okay.
there are some like harsh rules that they have put to use, so that
Yeah.
everyone gets are like every student over here are not getting affected. And moreover, really, the classes are going like in hybrid scenes. Like some people are coming because there's a huge issue on the economy, the educational
Right.
economy of United States.
Right. Right. Yeah.
And the
Absolutely.
other thing is that I have seen, like one of my friend who are coming here was coming here for PhD. He got admitted in a very good school in
Uh-huh.
US,
Mhm.
but he declined it and he rather went to Germany.
Really? Yeah. Well,
Yeah,
Germany has obviously handled this very well, right? So I mean, but
exactly.
I'm surprising. Wow. Okay.
Yeah, and because there they he said that I'm at least having face-to-face classes.
That's true.
So
That's true.
his session starts in November, so that's pretty well rather than staying in India and doing some remote classes.
Right. Yeah. 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 No, fair enough. So
Yeah.
Manas, I guess the folks are joining in now, and they're looking forward to your talk.
Okay.
And thank you for taking out the time to talk to this group here. This is going to be a bunch of students from Sabudh, like the
Okay.
last talk that you gave, but also we open it up, as you saw on LinkedIn and so on, for
Right.
people who are practitioners to register. So we will
Absolutely.
see people joining in. Thank you for picking a great topic. We've had a
Yeah.
couple of
Actually,
people.
it was something that I was working on for a couple of months back.
Right,
It's been
right.
like 5 6 months back when I started collaborating with some folks in India. So there's a startup known as Imbibe, which was
Okay,
recently bought by Reliance Jio,
okay.
and they were working on something very fascinating on education technology.
I see.
So I just thought of like I was reading some book and I was saying, oh, why not I know my research is on healthcare. Why don't I just paralyze with education technology?
Right, right.
So, and I saw that they have the same problem on explainability and interpretability, all those stuff. And so I thought like, why don't I write an article on that? So I wrote an
Brilliant.
article and got accepted in IEEE Internet Computing. And I got
Lovely.
your email and I thought, wow, that's a grand opportunity. Like I just put it out there.
Yeah, I'd have to say, I mean, I have a link with the IEEE, right? So they let me know whenever good articles are published.
Okay.
I'm only joking. But it is very opportune from the sounds of it. And we love the fact that we are going to be, enlightened with what you only recently published. So
Yeah.
look forward to that. And
Awesome.
why don't we make a start, right? And
Yeah.
people will join in as the
Sure.
talk goes along.
Definitely.
And
Definitely.
look forward to hearing you speak.
Right.
Over to
So
you.
how about like we can have, if someone has a questions, you can stop me in the middle,
Okay.
and I can answer the questions in the middle, or do you want to keep it at the end?
We are fine with if you want to take questions at the point in time, then I can
Yeah.
definitely kind of
Okay.
interrupt
Okay.
you. If you
Okay.
want to leave it till the end, we are happy with that as well. One thing I would say is don't rush for time, right? That we've got
Right.
to finish this in the hour. A number
Right.
of our webinars, because we are interested in learning, so a
Yes.
number of our webinars go longer than an hour. So don't get too
Yes.
worried about that. If it's pertinent, let's just discuss these things, right?
Okay,
Lovely.
absolutely.
All right. So do you want to share your screen, and we can just check
Yeah.
that the visuals are
Yep.
good? I'm sure it will be.
Yes. Let's say share screen, and I think it's pushing Adam. Okay. Uh, can you see the screen?
Super. Yes, I can.
Okay. Let me just remove this. Okay. Okay. So
All
you can
right. So
actually
over to
see
you.
in the presentation mode, right?
Yes, it is. Yes. Perfect.
Awesome.
Over to you.
Okay. Thank you, Sarab. So, okay, let's just, I think I just need to refresh it so that it loads pretty fast. Okay, cool. So, I would say good evening, right? Yeah. Good evening, everyone. So, today's talk that I'm actually thankful to Sarab for inviting me on this webinar, Data Science Pro webinar series. And it has been like a very interesting opportunity for me that I was working on some exciting article on that I just thought like it's worth publishing, and uh, and I got this opportunity to present this work. So and actually I just also wanted to share this thoughts and consider this to be like kind of an interactional webinar, I would say, and I'm open to any questions that you have, happy to address it, and feel free to stop me in the middle as well if you have questions. We will be going through a very exciting talk on interpretability and explainability. And the way I structured this talk for this today is more like a top down. So the definitions that you will be seeing on these very fancy and buzzwords will be pretty end of the talk. So just hold on to this, and I think it will be like more fascinating to learn something about knowledge graphs, deep learning, interpretability, explainability, and more of like why are we behind this? Why are we running after this? And that's because we want to learn some semantics of the black box. So that's the overall idea that I had in mind when I started this work. So actually, every exciting work you might be aware of starts with some kind of like a motivation. My motivation actually came from some of the non-fictional reading that I did in the past, which is one is the Flatland, which is about from uh, Edwin Abbott. It talks about the romance of the many dimensions. When I say many dimensions, means what does it look like when you have 100 dimensions of data? What do you look? How does it look like when you have 4 dimensions of data? What does 4 dimension represents? What does 100 dimensions represent? What is the computationally, what are the meaning? What is the meaning of these? Mathematically, what are the meanings of this? And there are some innate information that every dimension brings to your analysis. And so it is very interesting to actually see, let's say if I have 3 dimension, I'm moving on to the 4 dimension. The 4 dimension, what additional information does it provide to me? We learn about feature engineering, we learn about support vector machine and dimensional reduction and whatnot, and all these are actually nothing but the romance of the many dimensions. And this is exciting, and like there's a movie out of it and there's a book out of it. And I would encourage you to actually just at least go and see the movie. It's I think 13 years back. And the other one is this how not to be wrong. As the name says, that you don't want to be wrong, right? Just want to be right all the long. And there's a very interesting book which talks about some kind of counterfactual modeling, which is a very interesting part of explainability and interpretability. Though I didn't cover that in this talk, but I would urge you to actually look for explainability and interpretability in the explainable sections of the artificial intelligence. And this also algorithm also this book actually talks about another very interesting concept, that what you see in your data is not the complete information. There is some information out there which was used to construct your data, and you and your model are actually battling your brains against this data with a partial knowledge. You don't have the complete knowledge, and then you have latent representation, hidden representation, those kind of things, which tries to nothing but you just run after to find that inherent information that was used to construct this knowledge. In this talk, I would be looking at a more relaxed version of it, where Everything that was used to construct this data is given to you, yeah, is made available to you. So how do you use that? How do you use to the betterment of AI systems by bringing them the explainability and interpretability concept? So that's basically the two main reasons that I had this, like one reason coming from the romance of the many dimensions, the flatland, and the power of the mathematical thinking. So in this talk, I won't be going into details of the statistical learning. You might be very much aware of that. You have a data, you have a natural language pipeline with some state-of-the-art language models. You extract bunch of entities, which are nothing but the manifestation of the real world, finding the relationships, how those entities interact, events within the major event in where you are actually dealing with your problem. Contextual features means that some of the stuffs which are actually affecting the entities and the relationships within that event. So those are contextual features, and you pass it through a deep learning model, and you get some outcome which is weighted features and performance scores. But the controversiality that rises in the recent explorations by NIH, NSF, and all the big funding agencies is that we should not make black box model blindly. We should be actually focusing on how to understand the semantics behind the black box models. And then there is this a very interesting talk by David Cox on the neurosymbolic AI, which was the main crux of the entire conference in New York that happened, like the AAAI, the American Association for Artificial Intelligence, that has a very interesting series of talk, including the fireside chat with Yoshua Bengio, Lacun, and Gary Marcus, and Daniel Kahneman. So they actually talked about that why not we just wrap around the models, the data, around the knowledge from where this data is constructed, and models are pretty much aware of. And guess what? This is nothing new to us. It is already available. If we already know about it, you might be knowing in your early high school mathematics about the Bayesian theorems. And the Bayesian theorem is that you know your priors, you predict your posteriors, and you keep that posterior to become the prior for the next computation. And hence, so forth, you build a chain. And this prior is nothing but the knowledge that you have, right? And why do you need this knowledge? A very fantastic example that came from this adversarial network that you just let's take this example that is shown in front of your screen. Perfect performance by the actor. Every single word in the sentence has, like, say, performance is always positive. So by default it is positive. So you have a positive sentiment associated with it. Perfect has a positive sentiment associated with it. Actor does not have a sentiment, but definitely positive makes it positive. So you have a outcome as a positive. But if I move it like a spotless, spot and less. So less is actually a negative word, which actually dominates in its representation when you generate a representation of spotless in a distributed semantics. So the representation of spotless has a negative intuition that is captured by the model, and as a result, the outcome becomes negative, right? Or sometimes there is cases that the outer outcome becomes neutral. So there is this kind of a play of the words in the high dimensional space is kind of very weird, and it needs to be investigated further. So that's why they just blindly say that don't make black box models, because they are not something that you are very much aware of how they perform in the real world. Keeping this in mind, there are actually a bunch of articles that are actually coming out. Like, for example, the person tweeted about how the credit assignment happened, the credit score. Like his wife got a very high credit score than what he has, and something like Dr. Rudin from Duke University says that stop making explainable black box model in a high stake decisions, which is very much important, because when you're dealing in a high stakes, for example, racialism, for example, feminism, for example, sexist, for example, you can talk about radicalization, online extremism, fake news, misinformation. All these domains are high stakes. And if you just classify one person negatively, it has a huge impact on the community. So keeping in mind that you need to deal with some natural language carefully, you need to have a prior knowledge in front of you. You need to have a kind of a model that can digest these things together. That actually finds the core of my research in the recent past. And uh, and this set of knowledge that you want to include in your model occurs in a very diverse form. They occur at an individualized knowledge, that is every person has their own echo chamber where they find their comfort. And then there is a collective knowledge, where exam which is more like socially oriented, you how you interact with people, that is your collective knowledge. Then there is a common sense knowledge. Common sense means like you just things that you just know about it. You don't know the reason, you don't need a reason, but you know about it. But there is another set of knowledge which is domain specific. For example, making policy decisions, making whether this policy will be effective or not, making a system that will address in loan assignments and credit score definition. Those are like domain specific, a very that requires the knowledge of your expenditures, your transactions, and so on and so forth. And then there is the knowledge which is basically the norm. A norm knowledge is basically that you are actually having some social behavioral settlement, as well as your environment where you are actually dealing with. So these are another set of knowledge that actually comes into the picture. So when you have this entire set of knowledge which is being used to annotate your data, and you have the data in front of you, you just need to build a model that can actually bring these two things together to make more justified answers, more justified outcomes, and simultaneously give you an opportunity to understand what's happening inside the model, because you know the data, you know the knowledge on which this data has been constructed, and you're giving these two pieces of information to the model. So this actually forms a very clustered information, and actually that's a very interesting and a budding research topic in the current data science and machine learning community. And that actually forms my core research. And I'm Manas Gaur, and I'm a PhD student at the Artificial Intelligence Institute in the University of South Carolina. And I predominantly work around the intersection of natural language processing and knowledge graph with its application in machine learning. So, in this, at a very high level, today's talk would be more like bedside. It would be more, I would be giving like, it would be more like digestible maths. And what we will be talking about from Eagle's point of view is how do you integrate domain knowledge? That's the knowledge that you already aware of into your deep learning systems for interpretability and explainability. The way I structured this talk is, as I said before, is a top down. First, we will talk about what are the expectations that you can actually make from the deep learning systems, what you cannot expect from the deep learning systems, how does knowledge graph plays roles in the generating the explanations. Once you know that, how do you integrate this knowledge graph into the deep learning systems as well as evaluate it? And then you look at the knowledge graphs from its role in interpretations. Basically, how do you interpret the model? And finally, we'll talk about what do you mean by KG based explainability and interpretability, right? So moving on to the first section, which is no, not first section. Let's go back and let's just go onto a very trivial case of again motivational thought. Okay, let's take a trivial case of question answering with context. Let's say you have a context that I sometimes wonder how many alcoholics are relapsing under the lockdowns. So this is a very common context. Let's say one sentence, and the question being asked to the model is, does the person has addiction? And the model say yes, pretty easy, because alcoholic and addiction has a nice distributed semantics. You can use word to word, glove, BERT model to actually generate representation of alcoholics and addictions, and you can check the cosine similarity. It will coming out to be 0.7 and 0.8, which is way ahead your threshold, and you pick the answer, and the answer is yes. Let's twist this question to a more non-trivial case where you have the word depression in the context, but also you have a negation as well. Say that the person says, then others that insisted that what I have is depression, even though manic episodes aren't characteristics of to depression. So I do have a depression, but right now I'm facing manic episodes, and which are not characteristics of depression. So does the person suffer from depression? Right? As a part of the context, I would say no. But the model say yes, because the depression is an exact match with what you are asking the question and what's present in the context. And that's where you actually start to questioning your system, that what exactly it is attending to. Is it attending to the word? Is it attending to the phrase that would describe that word? Or is it would attend to a negated phrase that is actually describing the entire sentence or entire situation? So that is actually a non-trivial of question answering with context. And that's actually raises the question of what you can expect from your deep learning and what you cannot expect from your deep learning. And there are another bunch of questions that you can actually look for. Are you feeling nervous or anxious or on the edge? Is the feeling of restlessness due to stress or anxiety? Does an employee or own a company, or a person, or the person work for a company, right? So how do you distinguish between these two? And then you actually have, does shelter in place causes anxiety or prevents anxiety? I know that we know this, that shelter in place prevents anxiety, shelter in place is causing anxiety, but how do you actually make the model learn that causes is the right word and not prevents? So how do you make this kind of a disjunctive, how do you make the model able to handle this disjunctive queries? One such options are actually, one such work that has been done recently is on query to box and multi-hop reasoning, which is a way of delineating this complexity in the sentences and give a way of how you can actually box, create a bounding box around a region, and says that all the entities present in this region are the answers to your questions. So that is, rather than giving a point estimate yes and no, you kind of create a more like kind of reason oriented answer. So that's basically the research in which they're currently that's rising around this line of handling disjunctive queries, which is also the reason why, because this is actually help you in developing explainable and interpretable systems. So let's say talk about some of the open questions in deep learning that we have. Those open questions are expectations of what is possible from DL, right? Attention models as explainable systems. This is what is being considered so far, and there have been recent papers on talking about that attention is not what you need. Maybe some of the system you don't need attention. Why do you need attention in that model? Or sometimes you don't want the model to attend to something when you already have a prior knowledge or background knowledge. So expectations is what you need to actually address. You need to check whether your deep learning system is consistent in its performance, that whenever you are changing your domain from one section to another, the same explanation is happening. For example, let's say I talk about mm, autonomous driving vehicle in West Coast. So how about putting the same autonomous driving vehicle system in the East Coast? Does it perform similar way? What are the issues that it arises? How does model cope with it? Another issue, another case would be very simple. Let's say you go to a clinician, and you say, let's say you're going to 5 different doctors, and you give them the same information, but all of them gives you a different set of treatment. And here you are in a place where you are actually confused which treatment to take. Very similar to happened with the model gives an outcome to the 5 different people, and 5 different people have different opinions to it. How does model adjust to that so that it can give a most consistent information all the time? So that's a concept in research known as perceived risk analysis, and which is pretty interesting in understanding the complexity of the model. Now, then also we can say that, can we trim the complexity of the deep learning systems? That means that we don't always need larger models. Even smaller models does things. Like for example, you can simply say, sometimes say that, why do you need attention model? You can just simply use random forest or decision tree to solve this problem. So sometimes like the person is not able to give the right answers, because this is a question that you should always ask when you are trying to do a model building, when the problem are high stakes and explainable and interpretability is something that is you require. And then do we need huge deep learning systems with lots of data and lots of compute? GPT-3, which is right now the hot shot in the deep learning community. There are many works that have been pulled out recently, which just take 1/10 of the amount of information GPT-3 to solve some of the complex tasks. Definitely, they cannot solve all of them, but few of them. So definitely, you need to weigh whether you need a huge deep learning model or whether a small deep learning model will do well. Then we have another question, like, can we establish or maintain trust in the deep learning system? How often do you, as a user of AI, surrounded like by YouTube, Facebook, Amazon, follow their system recommendations? How do you cut their recommendation systems? Do you sometimes people shout out like, this Facebook or Amazon or YouTube are just tracking your things? Because like, do you really require that? So that kind of like a trust needs to be built in the deep learning system. The deep learning system should be able to give a response or give a recommendations, not based on your past history, but also your recency as well. So that thing needs to be taken into account in order to develop trust in your deep learning systems. And then deep learning model cost sensitive? So cost sensitive is very important topic right now, and it has to do very much with the high stake decision making. Suppose you are predicting fake news, and you predict a news channel as a news channel with a fake news. It has lots of consequences. So you need to weigh the cost of an error prediction in your model, and how well the model is doing in terms of those boundary conditions, and sometimes what the model does in a very obvious conditions. So you need to value the importance and the vulnerability of your model in these situations. So that's a motive behind, is deep learning model cost sensitive? So these all questions are actually, if addressed properly, will bring more closer the deep learning community as well as machine learning and NLP community more closer to an explainable systems, which you can actually reason about what's the outcome, whether that outcome is helpful or not. So moving on to the first section, after all this teasers that I have given so far, let's moving to the very core part of the work today's talk, which is on the expectations of what is possible from deep learning systems. So as I said, there will be a little bit of digestible math, and here it is. What can a deep learning system do pretty well? They can do function approximation. You might be very much aware of linear regression, logistic regression, lasso, ridge regressions are all function approximations, and it can model constraints pretty well. So what you have in front of you is an image that I took from a very recent and a very good paper from on deep fashion and learning. And there's another paper on that is in subsequence to deep fashion, which talks about the modeling the constraints. So what it does is that, suppose you have a target pose, that is the pose that you want your model to look at it, yeah, and you have an image. Looking at the target pose and the image, the model needs to generate some random images that would be in that particular pose. So in this thing, what they saw that it was taking a lot of time for the model to actually generate the right image. So what they did was they actually modeled the constraints. The constraints are like the shoulder, the twist of the shoulder, the length of the hand, the orientation of your eyes, and so on and so forth. These facial features, the body languages that is there, is are basically nothing but the constraints. So if you pose these constraints as rules in your model will be able to generate more closer images than just giving the target pose and the image, and allow your generative model to generate random images, because that images would not be able to comprehend what is the angle and what is the body posture in which the target poses. Because even the dotted points that you see, they are still like they are sparse. They won't give you complete information. So in order to move around in your high dimensional space, the flat land world, is you need to actually say that how these dimensions interact with each other. In order to facilitate that interactions, you need a constraint. So the constraints are nothing but rules that you want to just put inside to the model, so that the model can understand where to focus and where it can actually go with a little leniency, and it can afford the errors over there. So definitely you don't get the correct images, but you can actually capture the pose of the person. This was a very brilliant work on fashion technology that was done at CMU, and it talks about function approximation and modeling the constraints. Another thing that what DL can do pretty well is in terms of explainability is attention. I'm right now what I'm trying to say is all about explainability in the statistical sense. Let's go deep, as we go deep and deep, we'll go into the moving on to the explainability in terms of the more conceptual sense. Model attention. Models are the attention model that you might be all aware of, the famous paper. Attention is all you need. If it is given to a tweet, a text in a COVID-19 scenario, it tries to pick some of the phrases based on some stimulus. The stimulus is basically your outcome. What is your expected outcome? So based on your outcome, it will try to actually find the important phrases and give some values, right? And then there's a version of it known as a self-attention, which also pulls out these phrases and actually weights the edges between those phrases. For example, like COVID-19 is associated with unable to pay rent, but it is more important that if I associate lose their jobs, because the lose their job is a much more a costlier version than unable to pay rent. And that's actually we should attend to lose their job rather than unable to pay attend. So this is kind of a self-attention model. So these are like, I would say definitely there is a stimulus and you get this concept. But the question arises that would that if I say unable to pay rent is not there in the content, would lose this job will have the same high score? Like when you do an ablation study over your model, does the model perform in a very similar way or not? That's actually another question that will come up. That will actually come up in front of you when you put this model into a different domain, a different perspective where this data is not available. So that's another question that that explainability raises in front of the model attentions. That the attention of model is very much specific to the data on which it is being tested on, and does not bring in generalizability across multiple domains. Another thing that explainability can do for you, like the deep learning concept in terms of the explainability, is the ability to model the trust. And this is some a work that I would like to talk about as well, which is actually the work that I did in my back with my collaboration with University of Chicago. That suppose you have a patient, and a patient has clinician notes. Clinical notes, consider them to be a prescription notes that you get from physicians, and you pass it through a recommendation system, and the recommendation system predicts a series of clinicians. Now, which one of these clinician is important to you? You cannot ask the recommendation system; it won't tell you, because you don't know which clinician is more important. But how about you move a little bit, say that, oh, I saw this, I am a patient, and I see these three doctors, and these are my frequencies over the time, over the years. And I have this information, let's say I see the first doctor twice, where I also saw the third doctor once, and subsequently the next year I saw the first doctor twice again, but the second doctor I saw once, and then subsequently over the time I just kept with the first doctor because maybe he started doing pretty well. How about I model this behavior? And modeling this behavior is very easy. It is just kind of, let's say, the function that I show you. That is Tij. Tij is basically the time I saw a patient I saw a Dr. J, and it is nothing but a summation over all the different times you have seen a doctor, all the time that a patient I saw a Dr. J among all the possible doctors he have seen. And I just give a kind of a standard penalty function, which is e to the power of minus lambda t, which is just a penalty function that if I don't see the doctor again, I will reduce the weight of that person, of the doctor, by some constant. So that constant is nothing but 1 to the power of, let's say, alpha, just random number. And that 1 by alpha is just proportionating things down. And that is actually kind of like a penalizing option. And you just put that into a recommendation system rather than using this normal recommendation loss function. So you can get, let's say, you are able to model the trust. So this is a very simple way of inculcating into your model your behavior of how you feel towards a doctor based on his prescriptions. But let's move a little bit further on saying that whether that person, whether I know I saw this person multiple times, but definitely why did I saw that person, that doctor multiple times? Maybe he has given me a good medication. Maybe that medication was effective for me. How do I measure whether that medication is effective effective on me? The best way is that my severity of my disease is going down. That's most intuitive way. How do I model that? We model through in terms of ICD-10. ICD-10 is an international classification of diseases, and it has a kind of a code. And the fourth digit in that code is severity. And if that four-digit codes are going down, like consider this thing a very simple example. You might be aware of binary trees, right? As you go down the tree, the more number of bits you need to represent that information. As you go up the tree, less number of bits of information is you need to represent. Something very similar. If your severity is pretty high, you will require all the axes to represent it, and that is the severity. So if your severity is pretty high, that means all the four axes are filled. That means that your doctor is not doing pretty well with your diseases. And over the time, if your severity is going down, that means less number of bits are there. I would say that the things are working pretty fine. I just wanted to use that information that's also representable. I know the textual semantics theory of word to vec and globe or BERT, which can use to represent clinical notes, and I can model the trust. The model trust is basically the it can act as a bias to your feature vector. So you have one vector on your clinical notes, you have another vector on your ICD-10, and you have another bias vector on your trust, and you recommend the clinicians in front of you. So this time there's a possibility that only one clinician or two clinician is picked out. In this process, what did we learn? We learned that with trust I can do something better. I can actually model my movement, and I did pretty well. If you can see, I think the plots are not that much informative, but I would say, I would urge you to look at the 10 and the golden bar over there. It is pretty higher than what it is with trust, and what it is with trust in ICD-10. So definitely what we saw that by modeling the severity of the disease and modeling the trust in the clinicians, we are able to recommend over 80% of the patients with the right relevant primary care doctors. So which is way higher, way higher than what it is in the heuristic way, which is a random allocation that is being followed so far, and a version of a recommendation system which is called collaborative filtering, the CF. So what we saw that it is pretty interesting to model the trust and ICD-10 to get. Now if I recommend a doctor to a person, I know why I'm recommending it, because I can check the ICD-10, I can check the trust, and those two are a very fairly explainable measures to tell the person why I predicted what I predicted. And this work was actually featured in the Venture Beat to actually talks about that, because it was a very fairly actable, action-oriented, and deployable system to recommend doctors by modeling a trust in ICD-10 codes.
Manas, can I ask a question here?
Sure.
The recommendation that we are doing here is assuming that there is a general practitioner here. I mean, I could have multiple diseases that impact me, and
Yes.
I could be seeing multiple doctors for that, right? So how do we figure that out into this whole process?
So in right now in this, I will be talking about multiple doctors as well in the future slides. But this prediction was only for the primary care.
I see. Thank you.
Yeah, it is the first line of treatment when you feel sick and you want to talk to a person. The family physician is where you go, and suppose you have this general practitioners, and that's where we are looking at the recommendation.
Okay, great. Thank you.
Yeah. So with along this line of explainability in various domains, there is a very famous work on which is known as local interpretable machine explanations, which is LIME, which is basically a local interpretable model agnostic explanation. Because it is local, that means that whatever you have in your data, it is local to that. It is interpretable because you are actually making sense of these values. And model agnostic means whether you are taking the linear regression or logistic regression or any neural network or a complex deep learning network, it doesn't affect the outcome, because it is kind of a wrapper on the top of your deep learning model. So what it does is that whatever prediction that your deep learning model is making, you pass that prediction with through a linear regression model, and it can tell you why that model selected these particular features as important. So this is kind of, let's say, it is very similar to what you can say as a variable importance plot, or what are your target variables, and how does the model make a prediction of one particular kind given your data. So this is something very similar to, you can say that I'm passing my outcome of my deep learning model through a filter, and the filter tells me that, this is you have been given this label because these features in your model were pretty high weighted, and this you are given this feature because your model were pretty high weighting these features in its training side. So that's where the LIME works. So LIME is basically a way of kind of, you can say that, the outcome of your model, like let's say your softmax function, right? Before you put your softmax function, your output layer is a kind of a dense layer, right? Bear with me, like I don't have the architecture with me, but kind of like visualize it, that you have a very dense deep learning model, which is a bunch of layers. At the end, you put a softmax function because you want to just classify. Just forget about the class. Just forget about that softmax function. Just keep the last layer. That layer is nothing but a set of features that your model has generated. Pass that features through a linear regression, and it will tell you which features were important for your model and which features were not. And it can actually tells you that, and then you can actually make a more human oriented decisions with this linear regression model. So that was the whole idea behind the lime. But definitely it was, the lime was not actually the way it has to be. There were a lot of consistency issues. There were like interpretability issues in this, and the explainability is still not sure because you're still dealing with the numbers and you're not dealing with the knowledge, as what we talked about in the previous slide, where we had some kind of a knowledge in terms of an ICD-10 codes. Something along the lines, same with the lime, was the Shapley algorithm, which says that if you have a bunch of features, you pass it through a model, the outcome would be some kind of a variable importance plot or dependency plot, which tells us which variable is important, which variable is not important, given a data. And you can make a very fairly justification out of why the model predicted what it predicted. But still, it is way behind than your conceptual knowledge, which an end user would require. For example, let's say you put this model and it says it just punishes a one particular person into a prison, and the other person just leaves it, and he says that these are the factors. But if these factors are whether these factors are important to the stakeholders, the person who are judge or advocate, does this factor important to them, it is not aware of. So that kind of a domain knowledge is still not there in the SHAP, and that was the reason that it is still being used in some kind of application, but not in a high stake decision making. So this actually raises a concern of what we cannot expect from deep learning in terms of explainability. Let's drill down into this thing. I'm talking about high stake decisions for so long, for so like almost like how much? Uh, Maybe in like 40 minutes. So let's just talk about what exactly decision making means in high stakes. Understanding radicalization in social media. That is a high stake decision because a radicalization process and online extremism in social media is a very complicated research topic, because a radicalization or basically is kind of a brainwashing, or it's kind of like what do you call it, like you're luring. I would say like luring is the right word, because it's just like you're selling a product, right? So there's a multiple ways. When you open your Facebook, you see your Amazon Prime ads, and you scrolling the different types of shoes, different types of clothes, and that's kind of a luring. And you say, okay, I don't have the money, I don't want to do it. But they will show you the again those ads, and subsequent down the line you get lured. So you're actually moving from a different phases. Modeling those phases is a very complex process for deep learning, and that's a current complicated task of modeling those processes where a person changes drift from one place to another. And so far only statistics have been able to do it, and or you can do it with kind of domain knowledge, and it's very difficult for deep learning models. So but this is something that you cannot expect the model to do. Second, identifying emerging events during a national crisis. For example, you when we got to know about COVID-19, a lot of things were about Wuhan virus, coronavirus, China virus, all those hate speech, as well as those things started to bulge up. Hate speech is an emerging event. No one knew that COVID-19 will actually bring in racialism into the concepts. Another thing is the policies that the government started building. Business closures, school closures, hospitalizations, activities of daily livings were affected. So these events are natural, and they occur over the time as a pandemic happens or any natural crisis happen. How do you identify those events? It is very difficult for a model to understand because it doesn't have the knowledge of which event is important and which event is not. So there you need a background knowledge to actually tune your model onto a certain set of events that is important. And that's where the stakeholders role or human allied or human assisted learning comes into picture. Another is exogenous and endogenous spread of the disease. For example, let's take an example of the labor movement, the migrator movement in India. Suppose some workers move from one state to another state, may bring affection, may get infected over their journey, and can affect a lot of people over there. So that effect that this movement of people is bringing in is exogenous. It's not localized to that place. So definitely, in order to predict the likelihood rise in the cases in a particular state, you need to include both exogenous and endogenous spread of the disease. And that was the basically one of the work that I did in this year's KDD conference on how do you model these exogenous and endogenous spread of disease in the COVID-19, specifically in the India context, because there were two major events that happened. One was the Tablighi Jawad movement, and another was this workers movement, workers moving from one state to another state. So this actually brings in another question of what cannot be done in the explainability section. Let's take another example of a tweet. Let's say this tweet about flu pneumonia killed 6 times more people in COVID-19. If this information is given to given to the model will generate representations and make some predictions. What are the things that the model focus on? Kill more people and COVID-19, because these are the most commonly occurring terms in the phrases in the tweets. But are they really important to make decisions? I would say like more important are affected population and communicable diseases. But how do you get about that? So the theory of abstraction comes into the picture, that you have a graph. Let's say you talk about DBpedia, you talk about Wikidata, or you can talk about these kind of like gigantic graphs, or you can actually talk about, let's say, you can actually make your own simple own lexicons. Let's say I take affected population, I create a lexicon. Affected population means killing people. People got stuck. People got what you can say is claustrophobic. The people were actually the teachers were affected. The schools were closed. So some of the like affected population related terms can be bring together manually, and you can just simply use that to transform your data from flu, pneumonia, and COVID-19 and all those individual terms into just two phases: affected population and communicable diseases. And if you use these, your prediction is more meaningful than the prediction that is being made on some individual words. And now you can actually trace back why you pick an affected population and why communicable disease is more important in your prediction. So that brings more explainability. And there's something that the deep learning algorithm cannot do it on its own. There's something that you need to bring in into your deep learning setup in order to get a more explainable outcomes. Another thing that I actually was talking about the exogenous and endogenous spread is the explainability in the lockdown policy, right? People were locked down. They were actually they were locked in their state. I'm not talking about shelter in place. I'm just talking about the lockdown policy. People are following social distancing, and using this information, I use an SIR model, which is susceptible, infected, and recovered model, epidemiological model, to predict the likelihood, the movement of the infected people, the recovery people, and the susceptible people. Now, in this process, there is an exogenous people. Suppose there is a game that took place, and these people went there to see the game, and then they came back to the state. This set of information is not directly possible to be added into SIR model. And if we want to add it, what benefit are we getting? Check this out. So the benefit is that let's say this infection was peaking up at, let's say, 100 days. Over here, the infection peaks up around the like 50th to 60th day. That means the infection comes way earlier than what is predicted, and as a result, your policies needs to be more proactive than being actually defined by the normal SIR model. So your curve shifts a little bit behind, and your susceptibility curves also goes to normal earlier, and that actually tells you that the policies needs to be made proactive and more stringent than rather than waiting for the 100th day. So that's the idea of bringing the exogenous spread into the picture. And when you have this exogenous model, the first thing, the peak occurs earlier, and you know what event triggered it. For example, if I say the migrant workers movement did not, so it will give me the same infected curve as with the trigger event without the trigger event. So I can say that the trigger event was not important. But if it is, then we can say that which event was important, and the policies needs to be made in order to avoid certain events in the future discourse. So that's actually the idea of explainability, which is actually involved human into the picture, human in loop into your deep learning systems. Another case where that was actually coming out in the coronavirus is the question that came out in the Nature on whose coronavirus strategies were very much important and were more applicable. Like just like I in the beginning of this session, I was talking to Sarabhan that Germany did pretty well than on other countries. How about their using their ideology, their framework, their setting into some of the countries which are actually having a hard time coping up with the COVID-19 issues. For this study, what I did was I just took the Spain data and the India data. And the question that I asked was, why India surpassed Spain in the ranking of COVID-19 affected countries, though the India was not even the picture when the Spain was at the top. So what exactly I'm looking for? I'm looking for policy implications, and I wanted to look for the causality between the features. And the things, these two information cannot be derived from your deep learning model. So you need some kind of out of the box information in order to model these two things. And how do I do that? I just used a kind of a behavior people are expressing on social media, and I use that to over the particular time. So what I did was, I based on this the Spain and the India data, I was able to find the point of inflection, the point where the Spain started doing pretty well and the India was still started doing pretty bad, because India was not in the rank. It's slowly went into the rank. So I wanted to find the point of inflection. Once I found the point of inflection, I pick that date, I search the Twitter, I look at what people are talking about, what are the words that they are expressing, and I took that information, use their representation as a regularization into a deep learning model. Apart from that, I took a graph which is already created during the SARS pandemic by a domain expert, and the edges in the graphs, I took those terms and used those representations as another set of features in the regularization model. And I passed this to a simple linear regression, and I was able to find the impact of policies, and I was able to find the causality between the features. And that would actually tells me that what are the what I was able to see that over the time from April to May, there was hardly any change in the behavior of the people. Actually, that's a reason why even after inflection, point of inflection, the India started still going down in the recovery, and Spain did pretty well, because over there, over the period of from 1 month to another, there was sufficient improvement in the emotions and the sentiments of the people. So actually, you are, because epidemiological data would not tell you what are the policy implications, what are the causality between the features, because hospitalization, new cases count, recovery, susceptibility are all restricted to epidemiological data, all the SIR modeling. You cannot check policy implication or causality. If you want to do deep learning on that, you need to have an additional set of information for generating the explanations. And that was the idea of explaining the ranking of the countries in the COVID-19 context. Now, in so far, you have heard me about using the prior knowledge all along. What exactly this prior knowledge is? I just gave a very vague definition at the very beginning of this talk, that it is something that is not present in your data but was used to construct the data. And here is the definition that I want to give. It is the information external to the data set but used implicitly while constructing the data set. So you have some information in your brain when you construct the data set, but you did not document that information in the data set. So the data set is not complete. But at the same time, this information needs to be machine readable, and you can be thinking of this as a Bayesian prior, right? Some of the two resources that I would actually throw to you in front of you to actually look at and explore are the Wikidata dumps and the GitHub repository on the common sense reasoning. And a very popular knowledge graphs that have been used in the recent past are the ConceptNet, which is an open sense, common sense library that was started by MIT long time back, following the idea of semantic frames and semantic nets, a very old notion in artificial intelligence. And it is a pretty interesting graph that you can actually explore. FrameNet, on the other hand, is the modeling of the events. You can actually use it to actually see you rather pick the events from your content. Radiopedia is a huge database on radiology reports. So if you want to generate image captioning, you want to generate, let's say, which point of the image is important given the caption. Those computer vision related tasks, Radiopedia is something that you can actually explore. And ImageNet is already you are already aware of, is a bunch of images, but now they have completely converted into a kind of a knowledge graph by finding the association between the images. Now, moving on to this, like once we identified what exactly the prior knowledge is, let's move it to a more conceptualized, a more concrete definition of prior knowledge, the knowledge graphs. Because the information, if it is not a graph, it is just a delineated representation. And you need to explore the relationship in order to get a better explanation. So we will explore the need of knowledge graph in generating explanations from DL systems.
So this is a very concrete definition that I want to give it to you for the knowledge graph. It's a structured representation of a graph of basic your knowledge that is represented in many forms. For example, labeled property graphs, RDF. Yeah, by the way, you can actually use Python RDF lib actually to generate your own graph. And a graph nothing has nothing but subject, predicates, and triples. And these are the various set of ontologies and the common sense graphs that are created by various organizations over the time to understand various domain specific applications where as I said, information was used to construct data, but it was not documented in the data set. So you need these ontologies to actually make more sense to your data set. Another application where this knowledge graph can be used is a very interesting one, which I actually tested recently. Was, you know, BERT, right? You all are aware of Google BERT. It's a pre-trained model, right? You can use it in PyTorch or TensorFlow, and it has a very interesting library which is known as Vocabularytxt. So Vocabularytxt is a vocabulary list from the BERT. How about just add some bunch of terms that you think are important from an ontology into that vocabulary and just retrofit or reconstruct that word. So what you can do is that these words that you are actually putting in will actually align in a very magical way to find. And when you do k nearest neighbor clustering, just define the number of clusters or number of centroids equivalent to the number of new words that you added to the vocabulary txt. So what it will do is it has already know that bird has already a clustering framework in its mind. But when you manually feed these new clusters, it will orient in a different way, in a different way, keeping those words as a centroid. And you will find all the different words in the bird vocabulary to be aligned along these clusters, these centroids. And this actually forms a new version of BERT, which I call as a drug BERT, because I was using the drug related words. You can use any other terminology that you can find. And I just pass it through a BERT classifier, and guess what? I was able to find some of the important terms that is relevant for my decision making. And I just checked that I made some predictions on different countries, on how over the years, different states, how the over the years different states were actually having different types of informative drug abuse, depressive related thoughts because of the over selling of the news by the various news media agencies. And I kind of checked the ranking with the ground truth, which is nothing but the mental health America ranking system. And I was able to see that I was very much closely between the ranking, and it was kind of like the p value was pretty acceptable, was significant as well when I was checking. And it's a very minute modification that you're making into your deep learning model, but it does wonders for you. So because this information is not present in the data, I'm actually bringing in from the outside. Another application that you can actually look at the explanation over the clusters. So you have your data, you do neural parsing, which is semantic neural parsing is what you can get in Spacey as a very fascinating and a powerful tool. And to parse your content, and you use a deep clustering. Let's say you use a deep learning model to do a clustering framework, and you generate clusters. How does clusters look like? Clusters are nothing but a bunch of phrases being put together based on some distribution semantics. But when I say distribution semantics, bear with me. I think I didn't tell you earlier. Distribution semantics are nothing but word embeddings, and word embeddings are analogous to representation. So these all three phases are interchangeably can be used. So when you have these phrases, agitation, panicky, repeated panic attacks, all these words are actually assigned to a term known as anxiety, and this is what you get from a knowledge graph. And guess what? And then since these things are linked to each other, I can label this cluster as anxiety clusters. And this is what we call as a context understanding that you bring with the knowledge graph. This is something that is not there in the DL. This is what you need to in order to generate explanations. So you are actually bringing explanations through your knowledge graph into your DL systems. So likewise, similarly, that you have let's say you have a clusters in electronic health records, you do clustering in the social media data, and you want to explore that what are the things that are missing, what people say to clinicians, and what people say to social media, and what people hide from clinicians, and what people hide from social media. These set of information that you can use, you can extract, and then you can correlate between these two plots. So that's another application of using knowledge graph to generate explanations from your deep learning systems. Now we know how I talked about like how this knowledge graph happens, how this knowledge graph are what are its definitions, and how they can actually be benefited in benefiting in terms of generating explanations from your DL systems. Now let's just see if we how we can integrate them. I will give you like two or three I think strategies on how do you integrate them. Um, the first two strategies are shallow infusion and semi-deep infusion. So shallow infusion is basically that you have the data, you have a knowledge graph, and you combine their representation. First, either you can use arithmetic mixing, which is nothing but let's say alpha times of data representation plus beta times of knowledge representation. That's simply arithmetic, right? And you can define these weights. Another one is a concatenation operation where you generate representation of your data, you generate representation of your knowledge, and you combine them to you concatenate them and use a PCA or a singular value decomposition to generate a reduced representation, which is kind of a mixing only. Or other ways that you use a neural network function to do the mixing. So this actually generates a multiplex representation. So this, when I say multiplex, right, you know about multiplexer and demultiplexer in your electronics theory. Multiplexer are nothing but who mixes different types of informations, right? And they have a code. The code is nothing but the function, and the functions are invertible. So definitely, if you can deep multiplex, you can reverse that multiplexation to do demultiplexing of your representations, and which can be used in your downstream NLP task. So when you demultiplex, you can check from which part of the knowledge representation this prediction was made, and that actually brings us the explainability concept into this picture. Another one is basically the semi-deep infusion, where you are, so in the first one, bear in mind that you are all doing at the data level, whatever you're doing. You're not changing any loss functions. You're not changing any activation functions in your neural networks. But in the semi-deep infusion, you are actually changing the loss functions. You are actually changing your activation functions, and your activation functions takes into account both the data knowledge, data representation, and the knowledge representation. And that's why I call it as a modulated representation, because your representation that your models are generating at the each individual intermediate layers in a data network, it is modulated. And the modulated because you are actually fusing in the knowledge representation. Let's say three parts of your data plus four parts of your knowledge is given to one particular hidden node, and that on that three parts of your data and four parts of your knowledge, it is learning that relu or what do you call it, like leaky or sorry, relu or softmax or whatever function that you're sigmoid function that you're using to generate the activation for the next layer. So that's why you're modulating the representation at every layer. That's why I would say modulation. And that's a much complicated task than the multiplex, because over here, once you modulate, it is very difficult to demodulate it. So whenever you are using the knowledge representation, make sure you're checking at every layer. And that's what I will talk around in the future slides as well. And the another thing that it's a very complicated diagram. I understand that, but the takeaway from this statement is that suppose a student is giving an exam in the practice, and there's a practice questions, and the person is and the student gave a main test. They have individual features. The one I talked about, the shallow infusion and the thing, and the semi-deep infusion, all happen at this feature level. Nothing happened over here. But there's another concept known as deep infusion that happens over on the layer, and that's what I was talking about. That when you use this knowledge graph and the data, kind of an encoding into this together to actually affect the each and every representation of your hidden things. And what happens that now this model actually gives you an explanations. Let's say the weak concept, where the person is not weak in the physics, the person is weak in the math, and he also is weak in the behavioral parameters, like for example overtime incorrects or careless mistakes. So these points that you're getting are getting because of the stuff that are already present in your data lakes and your knowledge graphs, which you are using in your neural network. A traditional neural network will only give you that you are having a 71% predicted score in the JE mains, where the explanation will tell you what are the concepts you are weak and what are the concepts you are strong in, and actually what are the concepts that you need to learn. And this is a very fascinating explorative domain in education technology, and which is currently being used in Alexa as well, to which is known as deep knowledge tracing or Bayesian knowledge tracing. And the knowledge tracing is a concept, if you're going to look at it online. This is a very powerful concept in understanding what a student has learned by giving us a series of question answers. like giving an answers to for a series of questions. So here is it. So I just wanted to introduce Bayesian knowledge tracing. So the Bayesian knowledge tracing in this education domain is that infer whether a student has mastered a skill from a sequence of right or wrong answers to the questions that require that skill, right? So for example, you are being given a question, and you have given a series of answers, correct answers and wrong answers, then that will actually tell me whether you have mastered that skill, mastered that concept or not, right? So what does Bayesian knowledge tracing does? So this is without the knowledge graph, right? So what it does, it takes into account your prior mastery, basically a prior knowledge that I'm already aware of, that you are giving the exam on chapter number 10. That means till chapter 9 you have read it, so you know chapter till chapter 9 everything. So that means that I can use that as a prior to understand whether you will be able to success whether you will be able to complete the tasks, or the set of question answers in the chapter 10. Subsequently, I will also check over the time, how are you learning. So the I is the initial stage. As you address, let's say, 10 questions, what is your learning? As you address the next 10 questions, what is your learning? And so on and so forth. Your knowledge keeps on improving or degrading. I can actually regulate that. That's what Bayesian knowledge tracing is. And over the time, the prediction is whether you are right or whether you are wrong. And this is a very hard outcome. You cannot actually learn. You cannot help an instructor to understand how much the student has learned or how much the student has not learned. So consider this an example. Let's say you're being the person has been asked a question: what is the name of the compound after the addition of phosphate to glucose? And the correct answer is this. And the guess the person has made got happened to be correct answer. And the slip, if a person by chance slipped it, he says just say glucose phosphate. So when the person says a slip response, how can I say the student what went wrong, why the student went wrong at this particular stage, and what actually he should learn to understand? Maybe the model is not able to do that, and that's exactly one of the drawbacks of Bayesian knowledge tracing. Another question, there's another question the person has been given, and consider these two questions actually tells me that I can ask the third question: can we conclude from the correct responses of these two questions that the student knows phosphorylation? Can we do that? Bayesian knowledge tracing does not allow this particular questions, and that's the point where you can actually use knowledge graphs to understand that whether the correct answers of the two questions that the student has given, can I infer that the person has done a mastery on a particular small concept in that particular chapter? So that's where the idea, the key concept of knowledge tracing comes in handy. And those are the various research questions that are actually raised by various people, that the information which is required to enhance the mastery of a student is not present in the Bayesian knowledge tracing and the deep knowledge tracing. So the deep knowledge tracing and Bayesian knowledge tracing just differ in the model. Deep knowledge tracing use RNN, and the BKT uses hidden Markov model. So what additional concept are I'm actually trying to add? How I'm integrating the knowledge? I'm integrating the knowledge in the following way. Probability of a correct response given by the student is dependent on the concepts being mentioned in the question that you can actually extract through the entity recognition task in the NLP, which is pretty simple. You can explore through correlation matrices that you can actually construct between the concepts across various questions being asked by the student. And the third is that you can actually also create another correlation matrix between the concepts in the questions and the concepts in the knowledge graphs. And that knowledge graph can be constructed through various ways. And one thing that I did was use the EPUBs in the Amazon, the NCERT textbooks, and the books specific to the entrance exams. So I can use these knowledge I can just download this PDF and train my model to learn over this gigantic textual documents. And that becomes my knowledge graph for this context. And I have the concepts in the questions. I just find the cosine, the correlation matrix between these two. These values, these biases will actually affect my response and help me predict the explainable mastery of the student. And among all other education knowledge graphs, you can explore our mock, which is MIT mock. NPTL in videos can also be used as a knowledge graph in education. Udacity courses are already being used. Coursera, edX, Khan Academy is just recently they had released a paper on the knowledge graph in the education technology, and Udemy are also started working on the knowledge graph for the educations. Now, I have talked about integration of the knowledge in the past. Now, let's just talk about how do you evaluate. Evaluation a little bit differ than your precision recall and a mean square error based evaluation. So, first evaluation that are very prominently used is a statistical significance hypothesis testing, which is you predict an outcome and you check the hypothesis with the outcome with the true value and that with the, which with your knowledge that's actually the outcome, and see that how much are you doing pretty well with the real world information, and that's the statistical significance hypothesis testing. Another method is the inception score, and I would urge you to explore further because due to lack of time I won't be able to cover inception score. But the inception score in a very simple sense says that suppose you have 4 labels. That means that if you are using a GAN to generate some network, or you're using any deep learning network to generate some random labels, it should equally distribute its outcome across all the 4 labels and not only specific to only one label. So if you have 4 labels, then your lower score is 1 and your highest score is 4. And you have 3 labels, you have lower score is 1 and your highest score is 3. And that's what it shows in the plot on the right. Over the number of epochs of your training, I can see that over the time the model is able to predict the score between 2 to 3, 2.28. That means it is able to cover label 1 and the label 2. Definitely it is not able to reach the label 3, but eventually it will be having a score nearly 2.9 and 2.8 and above. So that is rounding up to the 3 labels. And the third point is TSNE, which is simply the visualization of the clusters. And the fourth is the human-centric evaluation, where you use crowdsourced experiment, user satisfaction, mental models, trust assessment, or correctability. These are all standard measure where you use Amazon Mechanical Turks to actually do some evaluation. So that's required in order to justify the explainability of your DL system. Likewise, there is a knowledge graph structure for explainability in the healthcare. For example, I look at this diagnostic interview between a patient and a clinician, and you can actually get this data publicly. It is publicly available. And the interesting question that I would ask, like I use a DL summarizer, deep learning summarizer, and it records that the patient has been diagnosed with PTSD when the script says the otherwise. The patient has not been diagnosed with PTSD. Why did it happen? Because when you use the knowledge, it explores the association between anxiety and PTSD and says that there is an overlapping symptoms between the two cases. As a result, if a person has been diagnosed with anxiety, there is a little bit substantial possibility that the person has been might be could have been diagnosed with PTSD and maybe he doesn't remember. That's why you have this chance. But this is actually it should be taken as a bit of salt that such summaries can have a detrimental impact on the person as well. When you say that no, you are actually you do have a PTSD when the person might not have a PTSD. So definitely these summaries needs to be evaluated by the domain experts. But this is one of the way of using the knowledge graph, and the more detailed evaluation of how this happened was actually is given in the link in the JMI preprint on how to generate abstractive summaries in such complicated communications. Likewise, you can actually use correlation matrices and variable importance plot. These are all forms of explainability, and you can actually use them to define because if the two things are correlated, and if the model predicts something because of that correlation, then you know that why the model predicted. So that's simply and a very intuitive way of saying the correlation matrices. And due to lack of time, I think I would not be able to cover this in detail. But you can actually look at the paper that I have given in the footnote, which talks about how this entire process happened, and it's a pretty interesting on this work. If you read it, just read it in a sense, looking at the zero shot learning concept in the deep learning and attention mechanism, because there's some modulation, some modeling of attention that happened over here, but that modeling of attention happened for using the knowledge graph and not the static attention or the probabilistic attention that is being defined in the attention model. paper. So I would actually give you a very simple delineated architecture of how this entire thing works. Is that you have an unlabeled data, or you have some set of data, and you have some knowledge graphs. You from that knowledge graphs, which is basically weak supervision sources, you can actually generate a labeling function. A labeling function is nothing but a correlation matrices. A correlation matrix is nothing but the concepts in your weak supervision sources and the concepts in your unlabeled data, and you find the correlation. And over this correlation, you're learning an optimizer that actually optimize this correlation to find that which particular point or which particular term in the unlabeled data is important with respect to the weak supervision sources, and not blindly. And then you use that to generate your random data and see how, and predict and do some predictions. And when I get some predictions, I can generate explanations because I know how this thing generated, I know what it did predict, and I can actually trace back to the weak supervision resources to say that why this prediction was made. And this was actually a work in Snorkel, a paper by Ratner and Back in 2017 and 2019 on this weak supervised learning in healthcare. Now, KG, now we have talked about explainability for long. I think it's quite a long time that we have learned detailed with many applications and explainability. Let's jump onto the interpretation. And it's a very, very critical that we separate these two phenomena. Interpretations and explanations are two different phenomena. This is what we have proved till now, that interpretations and explanations are not the same things. And the interpretations in the ML is completely different than the interpretation than the explanations in the ML, and that's what we will be taking away from this talk today. So interpretable ML methods, I will be talking about two of them. You can look for multiple of them along these lines. When you look along this literature, you can find multiple work on interpretable ML methods. One is a probing. A probing is nothing but a shallow neural network. It's a two-layer neural network stacked over your intermediate layers of a larger neural network to see that I just want to check that at every layer, I'm making sense. I'm making the right prediction. And what I'm trying to do is, if I want to predict the sentiment of a text as an outcome, and I know from my knowledge in my English, the certain post tags in English are very much important in order to justify the sentiment, then I would check that whether those post tags are being captured by individual layer of the neural network. If they are captured, I'm very good with the outcome. Outcome will be very much acceptable. But if those are not, then something needs to be done at the very initial stage rather than at the very end stage. And that's what probing does. Probing helps you to investigate at each layer that whether the layer is doing pretty well. And how it does through an auxiliary tasks. And auxiliary tasks are the tasks which a model needs to accomplish in order to accomplish a bigger task. So these are like kind of a subset task that you create. Let's say you say that in order to do integration, you need to learn how to model the functions. You need to know what is the continuity. You need to know what is differentiability, and you know what are the boundary conditions. And that's the only point after which you will be able to learn integrations. So that's the basically the auxiliary tasks. A very simple example of this auxiliary task are like, for example, I want to predict the next sentence. I need to understand the post tags, the dependency tree, the core reference, the nouns and the verbs of each and of the sentence. And I should predict that at every layer. And I should see that my model is not deviating too much from these things. If it is, then there's some point of information is being lost. So this is a very exciting work that took place on probing the BERT model and they talk about two types of probing: representation based and attention based. Representation based means whether representation is capable of preserving the information across the layer, and the attention is whether the words which are need to be attended to are being maintained across the layers. So that's the idea of probing, and it is one possible method of interpretations from a deep learning model. And likewise, there are fine tuning and multitask learning, which are other methods of interpretable ML, and they are or interpretable DL. Sorry for that. And they are actually so the only difference between these two methods are probes do not change your do not update your parameters of your deep learning model. It only tells you whether they are working pretty good or they are working pretty bad. Fine tuning and multitask learning are, on the other hand, allows you to change your update parameters over the time, and those actually are the, I think probes are not does not allow you to include knowledge graphs because they are predominantly just neural networks, whereas fine tuning and multi-class learning allows you to integrate the knowledge graph into your deep learning framework. So that's why they are more extensively used than probes. Whereas the probes can be used in terms of knowledge graph as well, but in that case, you have to give up on the neural network and just use the knowledge graph at every layer to see that whether your model is keeping up the information in the same way as it is shown in the knowledge graph. So that's why you can actually, that's where also you can use the probing. Another way of another form that I would not go into too detail, but you can actually look at it, is the knowledge distillation. So this is also another method of interpretations that was actually described by Hinton and all, which talks about that you can use a very a learned weights, a very big model to actually train us very small models. So, but the only issue in this case is that you are basically restricted by the amount of information that the bigger model has. It does not tell you, for example, like say outcome of sadness could be depression, but outcome of persistent sadness could also be depression. But if the sadness and depression relationship is defined in the teacher model and your question comes with persistent sadness, the student will not able to understand because that's not documented in the teacher. So that's a kind of a disadvantage of having teacher to student mapping, but it's a fairly good enough interpretation method because you can interpret those weights. Now, as I said in the previous slides, also we identify knowledge graph's role in interpretations. We know we identify the role of knowledge graph in explanations, and here we talk about how do you integrate these knowledge graphs into for interpretations. One thing is that what I told about the KGs for probing, you can use knowledge graph for probing methods rather than passing them to a deep neural network. What you do is you pass them through a knowledge graph and see how far or how close are the concepts in the representation domain. Suppose let's take an example. Let's say the person has abscess and angina are the two diseases the person is having, and the knowledge graph says that pain and redness and nausea are the three terms, and I know that the pain and redness and nausea are representation are there in the knowledge graph, and if the representation of the first layer is angina and abscesses, and I can find the similarity between these two and it is maintained in the first layer, I can go back in the content and say that whether the person over in the document mentioned about pain, redness, and nausea. If it does, I'm pretty well good that the model is doing pretty fine. But if it is losing angina or abscess or anything like that, I can figure out what additional concept I need to add on to this layer so that the model do pretty well over the onto the multiple layers. And similarly is the KG for fine tuning. For example, you have the data representation, you have knowledge representation, you concatenate, and that forms a KG BERT, which is also a very popular paper that was released recently in the AAAI 2020. So to sum up what we have learned so far is by giving you a concrete definition of explainability and interpretability, and how does knowledge graph plays a key role in this case. So I define knowledge graph explainability as the ability of the framework to compute the difference between learned concepts. When I say learned concept, means the concept that a model has learned through pattern recognitions and whatever the loss function that it has used at the representation level, and the actual concepts. So what you're trying to say, you're just trying to check the difference between these two. And this information loss is known as conceptual information loss. And that will actually tell me to what level of explainability is the model is having. If the model is diversing too much, I can actually figure out what I need to do. If the model is doing pretty well, I know why the model is doing pretty well. So that's a conceptual information loss. And now, how do I define interpretability? Is that so we define knowledge graph interpretability as the ability of the framework to proportionately propagate the conceptual information loss which you gather from the explanations among the hidden layers by modulating the hidden representations during the backpropagation. So everyone knows what is backpropagation. Backpropagation is the propagating of your errors when you are doing some prediction and you have the original y, y minus b hat is propagated back to the layer. But you do not want that error to be propagated equally across all the layers. You want them to be proportionately propagating across individual hidden nodes. So that's where interpretability comes into the picture. So when I say when I conclude my talk today, I would urge you to actually look for it, that interpretability is all about understanding the mechanisms of the deep learning model, and the explainability is all about the outcome of the deep learning model. And in order to achieve both of them, you need a knowledge graph or kind of a background knowledge to understand what the model needs to attend to, and based on that, how much of conceptual information loss is incurred at the output layer, at the outcome. So that's what KG interpretability and KG explainability means. So I conclude my talk with this takeaway on the definitions of KG interpretability and KG explainability. More information about which I didn't cover a lot of things. For example, the counterfactual part of the explainability as well. Some of the terms and some of the terminologies in the explainable models, like reasonability is another, completeness and coverage theorems, which are a part of the explainable stuff. But you can actually cover them. You can actually see them in these phenomenal papers. I would not actually, I put my paper over there. I don't consider it to be phenomenal right now. But these two are the remaining other very phenomenal papers on beyond accuracy, behavioral testing of NLP model with checklist, which talks about how do you evaluate NLP models, explainability and interpretability. And there's another work by Leilani and Gilpin, which talks about explaining the explanations, which kind of go give you a very overall view of what does interpretability in ML means and what does explainability means, and they actually nicely distinguishes between these two. What I gave in this talk is more of like the knowledge graph centric point of view, and as I said with the very beginning of this talk, that I am talking about a very relaxed version where the information which is already available is what you're utilizing in order to tweak the model parameters and making the model is more understandable rather than simply going blindly on the data sets. So there are some past tutorials that I have given on the similar talks on knowledge infusion, which is basically including the knowledge in your deep learning framework. And some of the things that I skipped over here because of time, you can actually catch up on these links that I have actually made online on YouTube. You can actually, I've just made a bit.ly links for just better understandability. So most of the work that I presented in today are actually some of the work that have been presented in some of the conferences, where I would say fact, I would urge you, if you are very much fascinating about explainability and interpretable and want to explore more ideas, FACCT Toronto, Canada 2021 is the right conference to actually look for. There are multiple works that are going on in explainable and interpretable AI. NIPS and KDD actually and the AAAI started focusing on explainable and interpretable AI from this year onwards. And if you have some work, these are the venue to go for. I would actually urge you. And also yearly, I'm actually organizing a workshop known as KIML, which is knowledge infused knowledge infused mining and learning, which talks about inclusion of these background knowledges in improving the framework of deep learning and how explanations and interpretations can be generated. Interpretations for the model, explanations of the model. And these are all the resources that I have used in my research so far in order to build this work on explainability and interpretability. And you can actually take a snapshot of it. And I think the video will also be, I think, will be coming on live. So you can actually take that from there. But these are, I think, something that you should actually explore in order to explore that what is this vague concept and the buzzword of explainability and interpretability and what exactly this means. And I also already gave you an idea that explanation is all about the outcome from the model and interpretation is all about understanding the mechanisms of the model. And thank you. And you can find me, I think that I didn't change. You can find me at https manas.github.io. Thank you.
Manas, thank you so much. That was an amazing trip through, very cutting edge topics, right, of explainability and interpretability of deep learning models, and a very relevant model. Of course, there's been a lot of questions around deep learning in terms of, how attacks on deep learning models can actually lead to very, unexplainable outcomes,
Right.
right?
Yes.
And so obviously, I think there was so much information there that I think people need to sit down and look through a lot of these resources. Thank you for those.
Yes.
Just if you can give us an idea of these knowledge graphs that you've been using here.
Right.
Clearly, are they human curated mostly? Are they is there mechanisms for generating these? And I guess if we had mechanisms for generating them, then
Yes.
we'll
Yes.
have general AI, right?
Right.
So what is the limitation there in terms of being able to actually get your hands on knowledge graphs in all domains that you're looking for?
So that's actually a nice question, and that's a question that I always get when I'm concluding my talk. And I apologize that I didn't take that into very serious account right now in while constructing it. But yeah, so there are some very big knowledge graphs that have been created over the time. For example, if you can see on my slide right now, ConceptNet is something that has been coming from 1990s. So it's been constantly updated over there, like almost like 30 years now. So they are already human curated. You can look at the Common Sense Knowledge Graph by Allen Institute of Artificial Intelligence, which is also a very starting work on creating this knowledge graph. Wikidata, which is already there, like almost like 3 to 4 years, is already a human curated. And there is another at the very end on the 16th point. It is an opioid drug knowledge graph, which is one of my friend actually constructed only to understand the dynamics of drug abuse in the United States. So these knowledge graphs, when you see, are first of all, the generic purpose graphs are almost created over the time, and they provide you general knowledge. And there are very domain specific knowledge graphs that you need to construct. And a very simple way that I follow to construct these knowledge graphs are that you have a large amount of textual data, and what you do is you pass this knowledge, entire text through a natural language processing pipeline, which extracts three things: subject, predicate, and object. Predicate is a relation, so you need relation extraction methods to extract the relations. And subject and objects are entities for which you need entity recognition methods. And once you extract these three things, what you need to do is you need to find that within the sentence, what is those triples, and you document those triples. And then what you do is you can store these triples in kind of a Neo4j or any database, graphical database, and you can then query it in just like a normal database queries.
Mm-hmm.
And the interesting thing is that also you can generate embeddings of these graphs, and these embeddings of these graphs are very specific to this graph, and you cannot simply use Word2Vec or Glow for it. And I think if I'm not mentioning over here, there are trans E and trans D are um, some of the common libraries that you can use to generate embeddings of these graphs. So that's how I think the knowledge graphs are constructed.
Yeah, that's great. In fact, this is so well timed because I think just last week, one of my guys in Patras gave a talk about knowledge graphs. And he's actually working on a live project right now to create a knowledge graph for all businesses, kind of looking in the government procurement side of things. So it's very timely, and thank you so much. I think you've done an amazing job of filling in so much information in that 90 minutes that you've spoken for. That I would love for you to come back and break it down into pieces and talk about. Some of the specific examples that you had, right, around, even you talked about the COVID example of trying to interpret. And I think that would in itself be an amazing, thing to delve into further.
Absolutely. I try to curve in the most, I just trying to like submerge all the math behind what was involved. Because I think it's pretty late, 6 p.m. and it was not the right time to put the math into brain. So that's why I just kept it as low as possible. But yeah, definitely I would love to give a deep dive on individual research topic that I projected today in the talk. And actually also the friend that you're actually talking about the financial, there is a very interesting ontologies that is right now people are building, especially JP Morgan, which is FIBO, which is financial business ontology. Yeah.
Financial business ontology, you said.
Yeah, it's called FIBO. And I think some of the people in JP Morgan are currently working on extending it.
Very interesting.
Yeah.
Brilliant. I mean, with something like the COVID example you were giving, right, where you were saying, why has India kind of emerged as, almost a victorious country in terms of
Yes.
this very poor ranking that we shouldn't want to be victorious on. But,
Yes.
there are so many different factors that impact that, right?
Absolutely.
So how do you actually get to encompass all of those factors? I mean, a lot of it may not even be represented, right, in any data or any knowledge graphs that we may have.
Absolutely.
So, I mean, are these kinds of studies always likely to be incomplete in the sense that, there are always other confounding variables that are out there, or, other variables that are not taken into account?
Absolutely. Actually, the question that you raised, Sarab, is exactly the response that I got from KDD.
Okay.
So the people over say that, how did you inculcate all this information in this one model? And I told them that this was not actually a very, it's just like I identified 10 features and I just put them into the model. What I did was I actually did an ablation study on this. I picked one feature and I added to the model and see how much improvement I'm getting.
Right.
And I'm justifying that what improvement I'm getting. Maybe this, for some certain features are not even relevant. Why do I put them into the model? So that actually was an iterative analysis that I did. And most of the time, what I try to do is I try to include behavioral features. Because if some pandemic or some epidemic happened or any crisis, I think behavioral features are more illustrative in the communications than simply some count based features. And that is actually what will actually make the model more nuanced and simply just a model running on numbers.
Right. And also, I mean, of course, there's a lot of talk about whether these numbers are really reliable, right? I mean,
Yes.
there's a lot of, at least, noise in India about, how these numbers are being fudged by people, either in one way where they're saying that, private labs are giving a positive result to more people so that they actually get people who were in contact with them coming to them for tests. At the same time, we also hear about patients that have been discharged before they died, just to keep the numbers lower, right? And even where people are being told that, the person died of COVID, but if you want his death certificate to say that, you won't be able to get access to the body for another week or 10 days, right? And so all of these factors in some ways make it impossible for data science here, and let alone deep learning, right?
Yes,
to really model these things.
Absolutely. And that's why, Sarab, that's what I was thinking of, I'm actually putting out in front of you, is that, that I talked about COVID-19, where I was using the external knowledge as a regularization.
Yes.
The idea was that I'm actually thinking of it, rather than putting as a regularization, I would make it as a main player in the prediction. And I put the epidemiological data as a regularization.
Right.
Because I'm not sure that how much I can rely on the epidemiological data. I'm not even sure how much it is correct. But I know what people are saying because people have seen those things. Right. So, but there is another issue that there is a fake news and there is a misinformation. Right. So you have issues on both the sides.
Yeah, I think the noise has taken over. Yeah, interesting. I think there've been a couple of questions during your talk which got answered. So, there's a, thank you for that kind of thing. One question that Achintya is talking, and I guess this is going back to looking at sentiment. How do you actually define weights to words that have both positive and negative meanings? Do you want to take that as a quick question?
Yes. So generally, sentiments are like the value of a sentiment, right? It is very much depend upon the context in which you are talking about. So sometimes, like when I was talking about spotless, the spotless word, if I know by default that it is a positive sentiment, I will just give the number. But if I leave that spotless thing onto the model will actually break that spotless into spot and less, because spot is a word and less is a word. And once you have a representation of a spot does not have any sentiment, whereas less has a sentiment, and that less sentiment has a negative meaning on it, and that takes the control over the entire sentence. So either you define a sentiment score for these complicated words, or when you are actually using them in the words in the sentences, make sure that you do not you are actually not splitting them into the spot and less, or making me are not using any NLP program that splits those words, because if you split it, then you just lose the sentiment of that word altogether. And I would actually try to diverge you to about two resources which I actually use in my research very often. One is LabMT, LABMT, which is Language Assessment by Mechanical Turk. So LAB, Language Assessment by MT is Mechanical Turk. And that is a very interesting resource of all the sentiment scores of these complicated words. Another is AFIN, AFINN, which is Affection Related Lexicon. And that also has a list of words of those words which you should not split and take their sentiment as it is.
What was the second one? Sorry, I didn't get that.
AFIN, AFINN.
Okay. Okay.
A for apple, F for frog, I for ice cream, and NN means neural network.
I see. Okay. Okay. Because you said something about lexicon and I wasn't seeing an L, so I thought maybe I'm missing something here. Okay.
So I generally use these because these are human curated, and I know which word I need to skip and which word I need to break.
So, I mean, are you assuming there that spotless was then a out of vocabulary word and therefore got split, or what is it?
Absolutely.
Right. Okay. I see.
So if you have an out of vocabulary, the model will by default break it.
Right. Right. Okay.
Because it doesn't have a representation of spotless.
Right. Okay. Brilliant. I can't thank you enough, Manas. This has been a great talk, and I'm really glad you could make the time to talk to us about this. I think you've done a great job as anybody who's steeped into this area and doing a PhD. To
Thank you so much.
Curate a great list of resources for everybody who is here as well. And
yes.
I hope that we'll be able to invite you again to come back and for you to take some more time out. I was just talking to Rai the other day, and I mentioned you had spoken to the students, and we are expecting him to come and speak soon on the series as well.
I would definitely love to join his talk.
I will let you know for sure. And so thank you again. And I know you've done so many wonderful pieces of work that are, and you alluded to some of that on radicalization and all of those pieces of work that are very social good related. So I really hope that, once the COVID situation is over, and I am actually in South Carolina, we'll be able to meet soon. And also, definitely. I hope that you'll be able to come in and even pick up some of those specific use cases that you worked on and give a more detailed talk on that. Thank you so much.
Absolutely, I would love to.
All right.
Thank you so much for having me here. It was a great pleasure talking to you all.
Yeah. All right. Thanks, man. Take care. Bye-bye.
Thank you.